Unit 6. Let's do a little review of sigma notation here. So when you see a sigma like that, it is identifying a sum. This variable, the dummy variable or the index, ranges starting from the lower value as the starting value to the upper value as the ending value. And this expression in here is a definition for what each term in the sum equals. So here, if j is going from 1 to 3, that's going to be 4 terms. 3 terms. 1, 2, 3. So we'll have 3 terms. In the first term, j equals 1. So then if I plug in 1 to this expression, I'll have 1 to the 5th minus 4. Here I've got, for the next iteration of the summation, j will be 2. So that's 2 to the 5th minus 4. And then last, 3 to the 5th minus 4. If you wanted to, you could regroup these as 1 to the 5th plus 2 to the 5th plus 3 to the 5th. And then minus 4, minus 4, minus 4. And even though this isn't what the question is asking, if you wanted to, you could rewrite these in terms of sigmas. So I could have sigma of k to the 5th as k ranges from 1 to 3 minus the sigma of 4 as k ranges from 1 to 3. So I'm factoring the negative sign out here, so I'd have minus 4 plus 4 plus 4. And then I could rewrite the 4 plus 4 plus 4 as a sigma, where that's the thing that I'm adding 3 times. Here I'm adding 1 to the 5th, 2 to the 5th, 3 to the 5th, and so I have my dummy variable as the thing being raised to the 5th power. I know that's not what the question is asking, but it's good to be able to know how to do that. It says evaluate by hand. It seems like not any fun. Let's not do that. You'll have calculators. It'll be fine. Another good thing to know is to recognize this pattern where you have -1 to a power of your dummy variable. You should know that that general pattern produces an alternating sequence of 1s and -1s. Let's go ahead and evaluate this. So k ranges from 3 to 7. So that's 3, 4, 5, 6, 7. So that should be 5 terms. 1, 2, 3, 4, 5. When k equals 3, k minus 1 is 2. And -1 to an even power is positive. So I know the first term is positive, but then the second term is going to end up negative, because in the next term, k will be 4. 4 minus 1 is 3. -1 to the third power is negative. So I don't even need to bother evaluating the rest of them, because I know that it's going to produce this alternating pattern here. So now all I have to do is think about the rest of it. Don't think about that anymore. Just think about k squared. So that's going to give me 3 squared. Well, here, let's not actually evaluate. Let's just write it in. This will be 4 squared, and this will be 5 squared, 6 squared, 7 squared. Nice. All right, so here we've got what's happening. Express each series using sigma notation, then evaluate. The sum of the first 12 terms of the geometric sequence that begins this. Okay, so let's write the sequence. So the geometric sequence starts with 5, then 15. And so because it's geometric, I know that each term is a constant multiple of the previous term. So I want to ask 5 times what equals 15? Or, in other words, 5 times r equals 15. And that would be true no matter what 2 adjacent terms I had in the sequence. I know the nth term times some number r is going to give me the n plus first term. So that gives you r as the ratio of one term divided by the previous term, which is sometimes why geometric series refer to the common ratio. It's because the ratio of a term divided by the previous one is always the same. It's constant. Okay, so that's 3, which you could have just seen by looking. So if I wanted to rewrite this expressing the structure more clearly, this is 5, and this is 3 times 5. And then the next one would be 3 squared times 5, and then 3 to the third times 5, and so on. So this would be 45, and so on. All right, let's express it using sigma notation. So I've got a sum. How many terms? It looks like 12 terms, so k will start at 1 and go up to 12. Is not the only way to do it, but it's certainly, I think, the most convenient. I've got 5 times 3 to the power of k. So well, that would be a very natural thing to write, but let's pause and think if that makes sense. So if I was going to evaluate it for the first term, I'd have 5 times 3 to the first. Oh, that's not actually my first term. So in my first term, I don't want to multiply by any 3's. So let's do k minus 1 up here. So that way when k is 1, k minus 1 will be 0. So this whole expression will become 1. So now when k equals 1, I have just 5 times 1 is 5. Then when k is 2, now I'm multiplying by 3. So you might need to adjust your expression a little bit to make sure that it works. So don't just try and write something down and then blindly run forward. You should always be doing little checks to make sure that what you're doing actually makes sense. All right, so that's sigma notation. What are we doing now? The sum of the first 12 terms. So I've given you these equations. In a regular year, I would probably ask you to derive these yourselves based on what we looked at in the video. So in one sense, you guys lucked out, and in another sense, it's too bad because you won't know stuff. Anyway, cool. So A here is 5 because A was our first term, and then R is 3. So you could use this equation. I think the equation is easier to remember as the first term minus whatever the term after your last term would be divided by 1 minus R. So my first term is 5. My last term would be 5 to the 11th power. So the term after my last term would be 5 to the, 5 times 3 to the 11th power would be the last term. 5 times 3 to the 12th power would be the term after my last term. And then 1 minus 3 is -2. And then, of course, you could figure out what number that actually was equal to, if you wanted to. The actual number is sort of less important. All right, so an arithmetic sequence, and we're given the 5th term and the 17th term. So it's like we've got a bunch of terms, and then eventually we have the 5th term, and then much later we've got the 17th term, and potentially it could continue. So an arithmetic sequence is a sequence where each successive term is a constant being added or subtracted from the previous term. So if we know that the 5th term is 204 and the 17th term is 408, let's think sort of how many times do we have to add something to get from here to there? So let's see. 17 minus 5 is 12. So that means there are 12 hops to get me from 5 to 17. So it's like 204 plus 12 times something. 12 times whatever our constant addition is going to equal 408. And now you could solve for k. I guess I might as well do that. So, all right, so 408 minus 204 gives me 12k is 204, and so k is 204 divided by 12, which is 17. Great. So we know every term is 17 larger than the previous term. So what that lets us do now is work backwards. So I know my first term up to my 5th term. So let's call the first term A. So I know that A plus 4 of my 17s is going to get me to 204. The reason why 4 of them is because here I'm at term 1. So that's 2, 3, 4, 5. So I have 5 additions to get me from term 1 to term 5. And each addition is 17. So 17 times 5 equals 204. And then we could do that. So that gives me my first term is 119. Okay, so we've done all of this various solving for figuring out what is the growth of the sequence and where does the sequence start. So if I was going to write the sequence from scratch here, I've got 119 plus, oh, now I have to do more arithmetic. Arithmetic's the worst. So I've got, 119 plus 136 plus whatever 17 more than that is, plus whatever 17 more than that is. So if I wanted to write this kind of broken out with its structure, 119 is my initial term, but then this is 119 plus 17. And then the next term is that one plus another 17, so that's 119 plus 2 times 17. And then the next one would add another 17, so that's 119 plus 3 times 17, and so on. So using a sigma notation then, what are we trying to do? The first 6 terms, so k goes from 1 to 6. Every single term has a 119 in it. And then it's also got some number of 17s. But the number of 17s in the first term is 0, so that's actually 17 times k minus 1. So that would be a nice way of writing it down using sigma. If I wanted to find the sum, the summation formula is first term plus the last term times the number of terms divided by 2. So for us, the first term is 119. The last term is 119 plus 17 times 5, because there's 6 terms, and so the last term I would have added 5 17s. And then divided by 2, and then times the total number of terms, which is 6. So you could simplify that, and that would be the value of the sum. So for problem 3, it's saying identify each sequence as geometric, arithmetic, or neither. So you know that geometric sequence has constant multiples that give you each new term. Arithmetic sequence, you're adding a constant to get each new term. And then neither would just be some other type of growth. So a very easy direct test you could use is choose 2 adjacent terms in your sequence and check what, like if you want to check for geometric, for example, you'd say what happens when you have this term divided by that term, and you get some number. And then you'd want to know, is that the same as you get when you choose 2 other adjacent terms? Because that would imply that you have a constant multiplicative growth. Same thing, if you wanted to check for arithmetic, you could check what's the difference between these 2 terms, what's the difference between those 2 terms, is it the same? If it's always the same, you know that you have linear or constant growth, which would be an arithmetic sequence. So for this first one, it might be, well, I don't know if it's clear to you or not. Each term is the previous term divided by 10, which is the same thing as multiplying by 1/10. So that would be geometric, except that I'm noticing this 0 actually doesn't fit. And this was probably a typo on my part, but that would be a great trick question on a test. The sequence as given would be neither. The sequence, if you removed that initial term, would be geometric. Let's take a look at this one. Well, here, let's rewrite this one. So this second one looks like it's sort of based on the first one, or at least I'm seeing a connection between the two. So the nth term of this sequence, if you remove this first one, would be 1/10 to the n. So if this is the first term, it's just 1/10. If this is the second term, it's 1/10 squared, which is 1/100th, and so on. For this one, it looks like if we were going to write it down, so it looks like this is a sequence, again, let's get rid of the 0. This is a sequence of the partial sums of this if it were a series. So in other words, this is equal to just the first term of the prior sequence. This is equal to the sum of the first 2 terms. This is equal to the sum of the first 3 terms, and so on. So the questions as I've asked them, A and B are both neither, but let's pretend that I asked them differently, and we've got no zeros here. In that case, A is geometric, and B is equal to actually the partial sum of a geometric series. What happened to the first piece of paper I had here? Is it on the, So because that's the geometric sum, because this is the geometric sum equation, this tells you the sum of the first n terms in a geometric series. So we could actually write down the equation for the nth term, and it would have that form. And that's pretty clearly not a geometric sequence itself. You know, I'm interested in sort of understanding what's happening with the sequence. If you just really narrowly wanted to answer the question without thinking any deeper, like there's a very easy, obvious thing you could do, which is what I said initially, just do this divided by that and observe that it's not the same as this divided by that. And that's enough to show you that it's not geometric. Okay, let's look at this one. Interesting. So I guess you can pretty quickly see that it's not geometric. Let's write everything under the same denominator. So this is going to be 30 over 9. If I do 30 over 9 divided by 41 over 9, that's the same thing as 30 over 41. And that's not the same as 41 divided by 52. So immediately I see not geometric. What about arithmetic? Yes, so 52 minus 11 gives me 41. 41 minus 11 gives me 30. So it does look like it's arithmetic with a constant decreasing growth of 11. Okay, so what about this one? Oh, so this one, so I'm noticing alternating negative, positive, negative, positive. And I also notice that we're multiplying by pi every time. So that seems geometric. And the growth would be multiplying by negative pi every time. All right, so here we've got an infinite series. It says express the infinite series as a limit of a sum. Okay, so what in the world could that mean? Remember that this is an infinite sum, but if we want to know whether this infinite sum converges, we have to look at a sequence of what happens when you add one term at a time, and those are called the partial sums. So just the first term is the first partial sum. The sum of the first two is the second partial sum. The sum of the first three is the third partial sum. So if you look at the sequence of those partial sums, you want to know, as you're adding more and more terms, is the sequence of partial sums approaching some fixed value? Because that would imply that the whole series, the whole infinite sum, is approaching a fixed value, and therefore it converges. So I'm thinking, all right, this is a geometric series. So how do you know what the sum of the first n terms in a geometric series is? It's this guy back here, the geometric sum equation. So it's saying express it in that way. So I know that the sum of the first n terms, well, here, let's decide what our various things are. So a is 3 and r is 0.28. So without writing a limit yet, let's just write the sum of the first n terms. So we've got that should be equal to the first term, which is 3, minus the term after the last term. So that would be, so let's see, we're imagining we're going to do n terms here. So the last term would be a times r to the power of n minus 1, but because we want the term after the last term, it's to the nth power, and then divided by 1 minus r, so that would be, I guess, the complement of 0.28, which is 0.72, does that make sense? Yeah, that makes sense. Okay, great. So this expression gives me the sum of the first n terms in that series, but I'm interested in what happens as the limit of the number of terms is, I'm interested in the limit of this as the number of terms approaches infinity. So that's what this infinite sum is equal to. It's the limit of this sequence. Okay, so does the series converge? The answer is yes, and the reason I know it does is this kind of simple test you can use. Whenever the magnitude of your constant growth multiple is less than 1, that implies that the terms themselves are approaching 0 fast enough that when you add an infinite number of them, the whole thing will converge. And what it converges to, well, let's figure out what it converges to by evaluating this limit sort of informally. I know that as n approaches infinity, if I have something smaller than 1 that's being multiplied by itself more and more and more times, it's going to approach 0, which means that this whole term approaches 0. So the result should just be 3 divided by 0.72, whatever that's equal to. Question 5, the graph shows the partial sums s sub n plotted against n for an infinite sequence. Okay. Does the infinite sequence appear to converge or diverge? Okay, so if these are the partial sums, that means that the y value here, this is like what happens when you add the first 20 terms of our unknown sequence. And this is the result of the first 40 terms of the unknown sequence. And this is the result of the first 100 terms of the unknown sequence. So it looks like as I'm adding more and more and more terms, the sum of all of those terms is actually approaching some horizontal asymptote, which would represent the limit of that sequence, which is the same thing as the value of the infinite sum. So yes, I think it does converge for the reasons that I just said. So estimate A1 and A2. So it looks like S1, hold on, S1 is 1. And it looks like S2 is what? Like 1.22 maybe? That seems very possible. So remember, S sub 1 is the sum of the first term in the series. So a sub 1 should just be 1. It should be the same thing as the first partial sum. The second partial sum is the sum of the first 2 terms in the series. So if I want to know what the second term in the series is, I'll take the sum of the first 2 terms, subtract the first term, and I should be left with the second term being just 0.22, which makes sense because we want each new term in this series to be smaller, approaching 0, because we know that an infinite geometric series only converges if its individual terms are approaching 0 fast enough. And this doesn't tell us if it's fast enough by itself. That you would need to look at this for. Okay, so this is about, can you think your way through just what is sigma notation talking about? So here I have the sum of the reciprocals of a bunch of numbers, and here I have the reciprocal of the sum of a bunch of numbers. So you could sort of make concrete sense of what this is saying with a tiny example. So let's say like n is 3. So on the left-hand side, we would have 1 over 1 plus 1 over 2 plus 1 over 3, because that's what this part's saying. On the right-hand side, we'd have 1 divided by the sum of 1 plus 2 plus 3. So, are these things the same? Hopefully you immediately say no, but if you don't immediately say no, no harm in just testing it out by plugging in some values, but I think very quickly you'll determine that those things are not the same. Find a function other than the identity function for which the... Oh, interesting. Great question. Okay, so... Oh, yeah, really good question. Okay, let's do it. So the first step in answering a question like this is tinkering with small cases to try and make sense for yourself of like, what is it actually saying? So let's do the same little example we did last time. Let's say n is 3. What this is really saying is we need to find some function f so that like f of 1 plus f of 2 plus f of 3, that's what it's saying on the left-hand side, is equal to f of 1 plus 2 plus 3. Okay, so you can now imagine a bunch of different functions. You know, I would probably like test out some basic families. So, you know, linear functions, quadratic functions, square roots, you know, all kinds of things. In the last problem, we saw that if f of x equals 1 over x, then this would turn into something that is not true. This would turn into 1 over 1 plus 1 over 2 plus 1 over 3, and we'd be asking, is that equal to 1 over that entire sum? So we already have one example of a basic family of functions where this is not true. But the challenge here seems to be, can you find some functions for which this is true? All right, well, the problem has told us I'm not allowed to use the identity function here, which is like a very simple line. So let's choose some other simple functions. What if I was going to choose, well, I don't know, let's do a different line. Let's do x plus 2. So if we've got x plus 2 on the left-hand side, we'll have, so like 1 plus 2 plus 2 plus 2 plus 3 plus 2, right? Because each of these f's I'm plugging in that input as my x value. And then on the right-hand side, I've got 1 plus 2 plus 3 plus 2 on the outside. So that one doesn't seem like it's worked either, because the 1 plus 2 plus 3 is the same on both sides, but here on the left-hand side, I'm adding 3 2's, and here I'm only adding 1 2. All right, well, you know, I really like lines, so because they seem like a very simple family of functions, and like some other ones that I can think of, like square root, are just like obviously not true. Like root 1 plus root 2 plus root 3 is definitely not the same as root 1 plus 2 plus 3. So let's try another one. Let's try like 2x, right? So what's that going to look like? That's going to look like 2 times 1 plus 2 times 2 plus 2 times 3. Is that equal to 2 times, that one does work. Cool. And you can probably see why it works, because you're able to factor out the common 2 here, and that produces the one on the right-hand side. So that immediately suggests an entire family. That would work. That would work. You know, any kind of proportional function like this would work. Looks like we got some combinatorics problems here, so I'm going to choose a group of 5 students, 2 girls and 3 boys from a class of 36. My class has 20 boys and 16 girls. How many different groups are possible? Okay, so if I'm selecting a group, it doesn't matter what order I choose the people in. All that matters is the people I end up with. There's some constraints, though. So some wrong ways to answer this would be to say I'm choosing 5 people and I've got 36 students, so let's do 36 choose 5. And the reason that's wrong is because that doesn't include the constraint of how many girls and how many boys. Another way that would be wrong would be to say, all right, let's choose 2 girls. So I've got, 16 girls. So that means I have 16 possible people I could choose for my first one and 15 possible people I could choose for my second one. And then for the boys, same thing. I've got, 20 boys. So 20 of them, any of them could be my first boy, and then only 19 of them could be my second boy because I've already chosen one, and so on. And so that gives me the total. The reason that one's wrong is because this is, so like, let's take the girls. If I have Anika and Anika 2, which are 2 different girls. That's confusing. Let's do another name. All right, so let's do Beth. All right, so here, this way of counting means that if I chose Anika first and Beth second, it's counted as different than if I chose Beth first and Anika second. But because all we care about is who we end up with eventually, we don't want to count those 2 as different. So if you wanted to do this laboriously by hand, you could divide by the number of reorderings that are the same. So here you divide by 2, here you divide by 3 factorial. And that actually would be correct. But that's the same as saying I have 16 girls and I'm going to choose 2 of them. And then multiplying that number of ways of choosing 2 girls by the total number of ways of choosing 3 boys, which is having 20 boys and choosing 3 of them. So this equation is the same as this equation, 16 choose 2 times 20 choose 3. And either of those is correct. All right, I got 52 cards. I select 3 of them to put in a line. How many orderings are possible? So this is like straightforward permutations. Here's my line of cards. How many choices do I have for my first possible card? 52, and then 51, and then 50, and that's it. And if you wanted to write this you know, for some reason as factorials, you could write 52 factorial divided by 49 factorial, because 49 factorial would cancel all the rest of the falling values here in the 52 factorial. All right, what is the coefficient for the term with y to the 11th in it in the expansion of x plus 2y to the 36th power? Great. So this is what we've done most recently. This is binomial theorem. So let's think about it this way. If I've got x plus 2y to the 36th, I know that I'll have x to the 36th plus some number of x to the 35ths times 2y plus some number of x to the 34ths times 2y squared, and so on. And then somewhere in the middle here, I'll have some number of x to the some power times 2y to the, what was it, 11th? Okay, and then the rest of the way. So I want to know if I'm raising 2y to the 11th power, which is what's going to give me y to the 11th, what are the other things in this term? So if you remember how we talked about the binomial theorem, if I'm going to expand x plus 2y to the 36th, that involves 36 x plus 2y's all being multiplied by each other, blah, 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 blah. And what happens procedurally if you were going to multiply all of these out is you're finding all the ways of choosing one of these two elements from each of the 36 terms to be multiplied. So it's sort of like you're multiplying each of these by all the other things in all the possible ways. So what that tells me, though, is kind of if you wanted to invent a new procedure, or if you wanted to treat this as a counting problem, whenever I'm doing, when I'm multiplying this out, I'm making 36 choices. I'm saying, for this particular multiplication, am I going to choose x or 2y? And for this one, am I going to choose x or 2y? Am I going to choose x or 2y? And depending on how I make my choices, I get a unique term at the end. So, for example, if I'd chosen x as the thing to multiply for all 36, that's what produces this x to the 36th. But if I wanted to know about this one, the x to the 34th, what I know is that in order to get 34 x's, for 34 of these 36 possible choices, I had to choose x. And that means I had to choose y for the remaining 2. And so that's why if I've got x to the 34, you know that the other exponent has to be 2. Because however many I'm choosing for the first one, all the rest of the 36 have to be for the second one. So in other words, these two exponents have to add up to my original power. So if this one's 11, you can immediately know what exponent has to be on your x because it's whatever adds up to be 36. So 36 minus 11 is 25. So that's a very intuitive way of thinking about what exponent my x has to be. What about that coefficient? So there are two ways to think about this. If I was going to have 25 x's, how many different ways could I have made my choices to make that happen? I have 36 of these terms, and I know that 25 of them need to be x's, so that's 36 choose 25. So that's what you could write as your coefficient here. A different way of thinking about it is I know that I want 11 of the 2 y's. So out of these 36 choices, I need to choose 11 of them to be 2y, and you could write that here. And these are the exact same number for a reason that we talked about in class. So that doesn't quite answer the question, though. So this is 36 choose 25. That doesn't quite answer the question because I want to know the coefficient of the x to the 11th term. And the coefficient, you usually group all of the numerical things in the front. So here I have a 2 to the 11th buried over here. So actually what I want to do is I want 36 choose 25 times 2 to the 11th. And this is the full coefficient on the term that has x to the 25th. Oh, you can't really see it, sorry. So what I've done here is I've rewritten this 2y to the 11th as 2 to the 11th times y to the 11th. And then I moved the 2 to the 11th out to the front because that's part of the coefficient. So that's actually the correct answer for the full coefficient, because everything else is just variables. All right, well, I hope that this was helpful. Good luck on the examination that we will do soon. And I hope that you are enjoying your indoor time.